Let's start the second section, which is talking about how to use the using of universal law of gravitation. Using the universal law of gravitation, first of all, in launching satellites. How to launch a satellite. Satellite is launched from the Earth crust. So we have the Earth's crust here, putting the satellite on a rocket, launching it, and throwing it in space. Satellite going to fall freely in a straight line beside the Earth's surface. Under the force of gravity, the Earth is going to pull the satellite towards. Now there are two forces. One of them is called gravitational force, and the other one is called centrifugal force. The two forces are equal to each other, and the two forces also are perpendicular to each other. The two forces which are perpendicular to each other and equal to each other make a state of equilibrium. But the state of equilibrium is going to make the satellite rotate in a circular path around the Earth. It's going to move in a circular path around the Earth and steady motion. Using the law of universal law of gravitation and also using the centripetal acceleration, خلاص A equal B square over R. We're going to find solving this equation together. The one which is saying that A equal B square over R, and the other one, we studied this law last year, and the one which is saying that F is equal to B M1 M2 over R square, M1 presented by Earth, M2 by satellite, and the last one, which is F equal M times A. So we have different rules to solve together, finally to have the velocity of satellite. The velocity of satellite is calculated using the following rule: V equal square root of GME over R. ME here is the mass of Earth. Why we choose mass of Earth, not the mass of satellite? In the previous lesson, we said that V equal square root G MS over R. We put the sun in the planetary motion. We put the sun, we choose the sun as the sun was the central mass. The greater mass which exists in the center should choose it to make it the central point, the central mass. Also, here in this rule, ME is the central mass, because in the motion of satellite, the satellite itself revolves around the Earth. So the Earth is the greater mass, is the one with the greater mass, and controls the motion of satellite. So I'm going to use the mass of the Earth and the satellite in the rule of finding even the speed or the periodic time. And to find the periodic time, the same rule of the previous rule of this last section, T equal to by square root of R cubed divided by GM. We have a proof for each of them, but you don't like to study. I'm not going to ask you about it, but we have different proofs. You are not required to study it, but I said inside the class already. The next slide, we have a problem to solve about how to find the velocity and how to find the periodic time of a rotation. I need here to explain something which is very important. V is equal to, V is equal to square root of G ME over R. G is gamma. G is equal to 6.67 times 10 to the power negative 11 plus Newton times meter squared per kilogram squared, or another unit has another unit, meter squared, kilogram minus 2, and second minus 2. One of them you can use that according to Newton's second law or gravitational law, universal law of gravitation. ME is the mass of the Earth, and I'm going to provide its rule of the problem. No problem. What is R? R is the distance from the core of the Earth, the center of the massive object, which is located at the center, to the orbital motion, to the line, the circumference of the orbital motion. So R now consists of two parts. One of them inside the planet, inside the Earth, and the other one outside the Earth. The one which is outside the Earth, we call it altitude, height. So to find the value of R, you have to add R of Earth, radius of Earth, and the height itself. By adding them together, you're going to find the R, which you're going to use to substitute inside the rule, using the rule. And also by the end, we're going to find direct substitution without write the unit while you're solving the problem. Don't write the unit, write only the numbers. By the end, you're going to find the mass, the velocity in meter per second. If you need to change it, convert it into kilometer per hour, we have a certain conversion. To convert from meter per second into kilometer per hour, you have to multiply 3.6. Change from kilometer per hour to meter per second, divide by 3.6. So we have conversion, but here we have two different units, meter per second and kilometer per hour. Meter to kilometer and second to hour. You have to divide twice, one of them for meter and the other one for second. So the division will be twice to divide mathematical calculation to divide 3.6 as a result. The second part of the question, he's asking about speed, and the second part is the periodic time. The periodic time is T equal 2 by the square root of R cubed divided by GME also. So we are able to substitute directly in this rule to find the value of the time, periodic time. But here I need to ask you to notice something. The altitude is presented by 450 kilometers. While you are solving, you have to change it into meter. You have to change it into meter because we are working in meter, SI unit, meter. Plus, you have to change kilometer into SI units or kilogram for mass, meter for length, and second for time. So you have to convert it into meter instead of kilometer. Here's the second part to find the periodic time. Free fall acceleration. What is the free fall acceleration? The word of free fall, that means the object falling down under the effect of gravity without mentioning the air resistance. There is no air resistance. The free fall acceleration, not all of the time, equal to 9.8 meters per second squared. Free fall acceleration can differ from one position, from one location, from one altitude to another one, from one height to another one. It differs. So we can calculate the acceleration by making a ratio between the radius of the Earth to the total distance from the satellite to the center of the Earth. يعني انا عايز اجيب الاكسلريشن هنا، الفري فول اكسلريشن، هيبقى انا عندي سمبلي كده بقول ار اي، ار اي is the radius of the earth. R is the total height from the earth center to the maximum height of the orbital motion. This ratio squared multiplied by g, which is 9.8, will produce the acceleration of our free fall acceleration. Astronauts in the space, we are able during the movie see that astronauts inside the space shuttle itself have uh, no gravity. There's no gravitational force applied on them. استنى كده يا مستر. No gravitational force applied on them, while the space shuttle itself is controlled to rotate around the Earth by force of gravity. The space shuttle remain at the same orbit under the force of gravity. The force of gravity controlling the revolving of this space shuttle. How come? The force of gravity affecting the space shuttle itself while don't affect the astronauts inside the space shuttle. The problem not in the gravity. The problem is something called contact force. In space, there's a lack of contact force. Contact force is the force which holds the object touching each other, holds them together, to keep together. In space, there is no contact force. So there is no contact between the Earth itself, which has the gravity, the source of gravity, and the object. So there's no contact force. Due to the lack of this contact force, astronauts have something called weightlessness. Weightlessness, that means they are able to move in different directions خلاص without weight. It's similar to an elevator drop suddenly down. The passenger inside the elevator feel for seconds, like they have something called weightlessness. They don't have weight because the contact force between them and the elevator vanished. Suddenly, they feel kind of free to fly. Here I prove that there's a gravitational force even at height of 400 kilometers, which is a satellite exists on this height, this altitude. The acceleration of gravity, make it acceleration of gravity 10, is 8.7 meter per second square. Yeah, this is a slight change from the Earth's surface. At the Earth's surface, G equal 9.8 meter per second square. At a height of 400 kilometers, 8.7. I don't think the small difference between the two values of acceleration of gravity. I'm going to know the next slide that's called the field of gravity does make the weightlessness. The one which makes weightlessness, the feeling of weightlessness, is the lack of contact force. The lack of contact force, not the lack of the gravity. The gravity already exists, and the force of gravity acting on the satellite or the station itself. Let's go to the next slide. We're going to use another expression to describe what is the meaning of the word of acceleration of gravity. We used to use the G for acceleration of gravity, 9.8. As a fact, G is not the acceleration of gravity. G represents the gravitational field. What is the gravitational field? Gravitational field is the area which is surrounding the object which has a mass. There's a field surrounded. During this field, inside this field, the force of gravity appears. So, during this field, all of this area, the force of gravity belonging to the Earth appear on any object located inside this area. By moving away from the Earth, the force of gravity, or the gravitational field itself, decrease. By the end, so far from the Earth is going to vanish. So the gravitational field itself is gm over r squared. Another rule to find the gravitational field. So now we can call G a gravitational field or acceleration of gravity. The rule which I'm going to use to calculate the acceleration of gravity is Gm over r squared. Acceleration of gravity measured by two units, one of them meter per second squared or Newton per kilogram. And the value of a gravitational field on the Earth's surface is 9.8 meters. The last part of our lesson, then I'm going to solve problems for the first section and the second section. The fact of these two kinds of masses. And the Einstein theory of gravitation. The two kinds of masses. We have two kinds of masses, inertial mass and another one is called gravitational mass. Inertial mass is the mass of object measured by exerting a force on the object and measuring object acceleration using inertial balance. Here we use the Newton's second law of motion by a force applied and a net force applied and the acceleration of the object. Object moves under acceleration, the speed change from one position to another, the acceleration, and there's a net force applying on the object. We also can use another force or another rule to find the mass. And here's mass is called gravitational mass. This rule is calculated from the gravitational law, universal gravitational law. Newton said that gravitational law or gravitational mass and inertial mass are equal to each other in magnitude. And this hypothesis, the way of making a thought is called hypothesis. This hypothesis is called the principle of equivalence. The principle of equivalence. Albert Einstein agreed this principle of equivalence and made a central point in history of gravity. This part is not so important because I'm not going to relate in this lesson the idea of the theory of relativity. This slide you only need to know these two types of masses. One of them is called inertial mass and the other one is called gravitational mass. And Newton said that they are equal to each other, they are equivalent. So this hypothesis is called a principle of equivalence. The last part of our lesson is called Einstein's theory about the gravity, and he mentioned that the light is a matter which has a mass, so there's a gravitational force between sun and mass, and it's also consider it not important. You have to read it only. You have to use this slide only because I'm not going to mention the idea of relativity now. After that, we're going to think about the relativity and what is the meaning of relativity in a different lesson, different section. So I'm going to explain it as a whole. Is it clear? I'll see you in the presentation, which I'm going to solve problems. So